Anytime.
Laboratory 3, unsteady state heat transfer. The objective of this lab is to examine the theoretical shape factors of an infinite cylinder, a sphere, and an infinite slab, and see how these interact in an unsteady state heat transfer environment. So what we mean by an unsteady state heat transfer environment is that we will be introducing these objects into an area of dynamic thermal non-equilibrium. So where in the steady state heat transfer lab, we establish an equilibrium before we take our data measurements. In this laboratory, we'll be taking measurements as soon as we introduce a delta T, and we'll be monitoring until we achieve equilibrium. It'll be, in this case, we'll be placing 3 objects at room temperature into a kettle boiling with water at 100 degrees Celsius. This will allow us to examine the temperature of these objects and the gradients of temperature throughout these objects as they come to equilibrium with the 100-degree boiling water. So, the way that we're going to achieve this is downstairs we have a large 30-gallon kettle. It's a steam kettle. The steam will be generated within the jacket of the kettle automatically. The steam pressure and the pressure will be recorded on the wall of the jacket. You'll be able to read the temperature and then ascertain the amount of steam, assuming saturation. This temperature gradient from the steam jacket wall to the water within the kettle will be more than sufficient to keep the water boiling at 100 degrees. Now, once we have achieved 100-degree water within the kettle, we'll be placing each one of our shape factors into the kettle and recording the temperature throughout the object. Within each object, we have embedded a T-type thermocouple. That's a copper constant thermocouple, which will be reading continuously through the use of a thermocouple reader. Now the thermocouples will be embedded at various positions within each shape factor so that you'll be able to describe the temperature gradient as it moves throughout the object, both experimentally and theoretically, and then compare the two. Now, the data and the formulas given to you in the lab manual describe an infinite slab and an infinite cylinder. We don't have infinite cylinders, obviously. We have finite objects. Your job will be to compare how these theoretical formulas contrast our theoretical infinite objects that they should be behaving to how they're actually behaving in real life, and explain any discrepancies. In order to get engineering units from these thermocouples, they're going to have to be calibrated. These are handmade thermocouples, as you'll notice when you go into the lab. And therefore, when we first turn on the thermocouple readings, there might be some discrepancy in the units given. For instance, when you first turn on the thermocouple, we might have a reading for room temperature of 22.1, 21.9, 22.4. This is normal. You'll have to take these values and calibrate them. The way that we're going to calibrate them is by immersing the thermocouples into a bath of ice water, which we can assume will be 0 degrees Celsius, and boiling water, which we assume can be 100 degrees Celsius. Now, any offset from these values, for instance, 0.4, 0.6, -2, and 101, 98, you can calibrate each thermocouple by basing it off of these absolute measurements. We know that these are theoretical constants, as ice water will be 0 degrees until all of the ice is melted, unless there is any gradient within the system. Similarly, water at 100 degrees and 1 atmosphere will boil at 100 degrees Celsius. Therefore, we can use these 2 points to calibrate our thermocouple system. Once our entire bank of thermocouples has been calibrated, including one to simply put into the water to measure the environmental temperature, and one to put at room temperature to measure the room temperature, we will then immerse each one of these into the bath and begin collecting our data continuously. It's imperative that you have all of the temperature measurements monitored as quickly as possible so that you can see the temperature changes over time and ascertain the shape of the curve. Most heat transfer applications you encounter in industry aren't at steady state. you'll be in some type of thermal non-equilibrium, which you'll have to account for. Often, shapes aren't ideal. For the second part of this laboratory, we're going to be immersing a potato, an irregular shaped potato, into our water bath, and we'll be observing the temperature gradients within the potato and comparing to our idealized shape factors. The way that you're going to do this is the flesh of a potato, the starch, will begin to gelatinize at a very specific temperature, and you can watch this gradient pass through the potato as time goes on. At certain time increments, we'll be slicing the potato open and observing the starch gradient as it moves to the center of the potato. We'll then attempt to determine when that gradient will come to the center, and we can determine whether the potato is fully cooked. This is a very simplistic application of thermal non-equilibrium, but it will give you an idea of how this application can be presented into industry applications. In conclusion, you will use the 3 equations given to you in the manual to determine, with the characteristic distances measured in the laboratory, the delta T measured from the beginning of the experiment until the end, and you'll determine theoretically how the heat should be penetrating according to theory. You'll then compare your experimental data to these theoretical applications and look for any discrepancies therein. Laboratory 3, unsteady state heat transfer. Here we are with the apparatus for the unsteady state heat transfer. We'll walk through each aspect of the apparatus in a second, but first we want to talk just a little bit about the safety in this lab. We're in D117, which is a food science pilot plant, and it has slightly different safety considerations than the other chemical engineering pilot plant. For this laboratory, you're going to require your laboratory coat and your safety glasses. However, your hard hat and safety shoes are not required in this laboratory. This is the home of both the unsteady state heat transfer and the spray dryer lab, which you'll be completing in the winter section, or 4802. So with this laboratory, we're also going to require the use of thermally protective gloves. We are working with scalding water, very high temperature steam, and of course, other people working in the vicinity around us. Always remember to take into consideration other laboratories that are being performed at the same time yours is, and not to interfere with the other machinery or equipment, even if it appears to be inactive. A lot of the experiments performed in this laboratory are long-term experiments, and they may be actively ongoing or taking measurements, even though there's not somebody actively monitoring them. All right, so what we have here is, as we discussed upstairs, our steam kettle. Currently we have it in operation, so the steam jacket, seen by the bulging area here, is now very, very hot. The steam within is currently at about 22 psi, and based upon your steam tables, you'll be able to determine what temperature, assuming we have saturated steam. When this cools down, incidentally, the steam will begin to collapse back into a liquid and will actually form a small vacuum within this steam jacket. When you come into the laboratory, the apparatus should be already started, because it takes a bit of time to bring the water up to boiling. However, if you are the TA, or if you're coming into a cool water laboratory, you must first turn on the main power switch for the kettle, which is located on the wall behind me. Secondly, you must turn on the main power here and set a set point here for the temperature. This is not an engineering scale. It is simply a relative 0 to 10. It will not give you a specific temperature. It'll simply provide X amount of energy into the steam jacket, and you'll have to ascertain how much is sufficient to maintain whatever temperature that it is you're looking to maintain for a given load within the kettle. Our current load within the kettle is water, which we know at atmospheric pressure will boil at 100 degrees Celsius. We can slightly put a little bit too much energy into the jacket, which will maintain our temperature within our environment at 100 degrees for the duration of the experiment. We want to keep a rolling boil, but not excessively so. As you can see now, with the amount of water vapor coming off of the kettle, that we have a very good rolling boil. Therefore, the temperature within the unit should be 100 degrees Celsius, for which we'll test in a second. So, our next piece of apparatus will be the thermocouples that we'll be using throughout the experiment. Now, during your actual experiment, all of the data from all of the thermocouples will be collected continuously. You'll then be responsible for taking this continuously collected data, whatever frequency the sampling is at, and build that through Excel into all of the theoretical formulas, and then compare the experimental data to the theory. Now, if you can take a look at one of the thermocouples, we've chosen T-type thermocouples as the temperature range will be adequate for this experiment. This thermocouple, as you can see, is very inexpensive. It is simply the two pieces of copper and Constantan wire welded together and connected currently to a thermocouple reader. It is currently reading the ambient temperature of the air around us. It's a little warm. We're filming in the summer, so it's reading at about 24 degrees. You can check to make sure that the thermocouple is operating correctly by simply holding it to your skin, which in my case comes out at about 32 degrees Celsius, blowing on it, or submersing in ice water. Now, during the calibration, you'll be doing a 2-point calibration between a bucket of ice water, provided here, which, as discussed upstairs, should give you a temperature of exactly 0. We'll allow some time for the temperature of the probe to come to equilibrium with the bath. And once it has, we'll recognize that there may be an offset between the value given by the thermocouple and what we know the temperature of the bath to be. This offset must be corrected for by calibration for each one of the thermocouple probes, as they all have a slightly different offset and all require slightly different calibration. Once you have the absolute 0, or the 0 degrees Celsius temperature for each probe, you'll also be using water at 100 degrees Celsius to perform the high point of the calibration. In this case, we have our boiling water. We will don our thermally protective gloves. And after submersing the thermocouple into the water, we should be reading very close to 100 degrees Celsius. In this case, the high point of this particular thermocouple is exactly on, or off by a very marginal amount. There will be some flux. Try to take the average value over time. This will be aided by the fact that your data will be continuously collected. Each one of the shape factors given to you will be made of one of two materials, either a high density resin or a low density body fill. Each one of these will have different thermal characteristics. Part of your job in your report will be to determine what the thermal diffusivity or conductivity of each material is for the object. You'll be aided in that you'll have several different shapes. These will be your cylinders. You also have spheres and your slabs, and you'll have thermocouples positioned at different points. The thermocouple, as you can see in this one, is embedded directly in the center of the object. When the center of this object reaches 100 degrees after being plunged into the kettle, at that point you'll be able to pull it out and you can assume that you're at equilibrium. You'll be conducting the experiment for all of the shapes all at once, and it will take some time for the thermal gradient to pass all the way into the center of the object. Okay. Once your water is completely boiling, you've calibrated your instruments and you've determined the ambient temperature of the air, which will serve as your delta T. We'll be putting in these objects at approximately, if we look at one of the objects, this object corresponding to this channel is currently at 25.9 degrees Celsius. We'll be plunging this into 100 degrees Celsius and waiting for the very center of that object to come up to 100 degrees. Now we're ready to plunge the shape factors into the boiling water, and we've also added into the apparatus one thermocouple which will keep a continuous track of the water temperature, in addition to one thermocouple existing outside of the apparatus which will keep track of the ambient air temperature. In this case, we can watch as our thermocouple attached free-form in with the shape factors dramatically changes from the ambient air temperature up to the boiling water temperature. At this point, make sure that you have someone starting the timer so you know exactly at what time you begin and at what time you end. We can see that almost immediately the temperature reading for the thermocouple, which has no thermal resist or very little thermal resistance, immediately shoots up to the water temperature, whereas the temperature of the first object, while slowly increasing with the highest delta T, will slow down the temperature gain as the delta T diminishes. While the temperatures are rising, we're also going to talk a little bit about the report. So in this report, as we've stressed again and again, the most imperative aspect is to compare your data to the theoretical, what you'd expect to find. Now we'll talk a little bit about the report. Now, in this report, the discussion is the most important section of the report and will be weighted accordingly. We want you to talk about any differences that you see between the theoretical and the experimental and why these differences might exist. After this, you can talk about some of the practical applications of this theory in industry and in other areas of science, any application that you can think where you will be applying some of the theory that you've learned in this laboratory.